Swayam Prabha. Digital India. Educated India.
Hello and welcome to week 7, which will introduce you to the reinforcement learning problem, which is what's going to take up most of our attention through the rest of the course. So in this somewhat short video, I will do 2 or 3 things. First is to formalize the reinforcement learning problem, which basically just means putting together what we've done so far with MDPs and bandits, and then tell you a little bit in detail about the topics, okay, the sort of table of contents for the rest of the course, the ones that we are planning to cover, and finish up with giving you once more taste of applications. Okay, we did this with MDPs, but then I'll also point you to some references where solutions are designed using reinforcement learning so that you can connect up the theory with the practice as we go along. Okay, but let's begin at the beginning. What really is the reinforcement learning problem? Here's what it is. Okay, so there is an MDP. In fact, this is the one that we've been looking at as a running example. So let's just consider this MDP. So there is an agent that is interacting with this MDP. Okay, as we've seen in the past. So it's in different states. It takes actions. If it does that, it's going to get rewards and go to next states based on the underlying MDP. Okay, and it wants to maximize, let's say, expected long-term reward with this particular discount factor 0.9. The main difference that we have to accommodate in the reinforcement learning problem is that the agent does not know the underlying transition probabilities and rewards. Okay, so the agent's view of the world is what is shown on this picture. Okay, so the agent knows that there are these 3 states and these 2 actions, let us say. All right, and it's also told that the long-term reward that we want to maximize is expected long-term reward, let's say with a particular discount factor. Crucially, the agent does not know that the transition probability of action read from S1, right, is half to S1 and half to S2. Okay, so sometimes it's reasonable to assume that it might know associated rewards. Right, the agent knows the reward function. Sometimes even that is not known. Okay, of course, at any point of time, the agent knows in what state it is. Okay, so the agent is really not in a position, without knowing what the transition probabilities are, to decide what is the optimal thing to do, right? So we know that if you're given the entire MDP, you can plan, right? You can use value iteration, policy iteration, linear programming, and compute pi star, and presumably the agent can thereafter start acting according to pi star. But what to do if it does not know t, right, the transition function of the MDP? So it has to make do with whatever it has, right? So whichever state it is in, the agent, its job is to take an action, so it will take an action, right? Let's say one way or the other it takes an action. But when it takes an action, the world does what it does, right? It takes the agent to a next state and gives it a reward. Now, this next state and reward are indeed drawn according to the underlying transition probability and reward functions. Okay, so the MDP is still behaving consistent with, there is a fixed underlying MDP, which the agent does not know, right? But now that it has had this one unit of experience, right? From this state, it took this action, it went to this next state, and it got a reward. Now, this constitutes a little bit of information for the agent about the MDP. Okay, it knows that from this particular state, when I take this action, this is something that happened. Okay, so as the agent goes along, it is going to gather a trajectory, right? A sequence of experience. So, for example, on this illustrative MDP, one possible history that can unfold. I mean, we call it history when we're looking back at it. So going forward, maybe you want to think of it as a sequence of interaction or a trajectory. So let's say that the agent started in state S2. The agent takes action red, let us say. Okay. Now, what's going to happen if you take action red from S2 in this MDP? With probability 3/4, you're going to go to S3, and with probability 1/4, you'll go to S1. Right? One of those 2 things must happen. This particular time, what happened is that the agent went to S3. Okay, so this is something that would have happened with 3/4 probability, and let's say it's what happened, and the agent got a reward -2 to go with that. Now the agent knows that it is in S3. It also knows whatever it has seen so far, right? It knows that from S2 I took red, I got to S3 with a -2 reward. It can use that if it wants. All right. So maybe the next time it goes to S2, right? It has a little bit more information than it had last time. From S3 again, it's got to do something. So let's say it takes blue, it goes to S1. In fact, this is the only thing that can happen, right? It goes to S1 and gets a reward of 1. I mean, us looking at this picture actually know that S3 going to S1 by blue, right, is the only thing that can happen if it takes a blue from S3. That's because we know the MDP. The agent does not, right? It has to be open-minded about blue being a possibly stochastic transition, right, with probabilities of going to the other states as well. Okay, but maybe over time, right, it will figure out that this action always seems to be taking me from S3 to S1. And then from S1, it takes a red, etc., and you can see what's going on. So the point here is that what it has seen so far, right, the sequence of interactions that the agent has encountered, or the history, right, that conveys some information about the underlying MDP to the agent. And the question is, with enough such information, if it lives in this world long enough, with a long enough history, will the agent eventually be able to take optimal actions, right? Our original problem with MDP planning was to take optimal actions, right? We knew that there was an optimal policy, we wanted to find it, so we computed it. Here, you don't have all the information that you need, right? So the reinforcement learning problem is really the process of trying to gather that information based on which you can thereafter induce optimal behavior. So is this possible? Now, clearly this is not possible right away, right? But it seems like with more and more and more time spent in the world, right, you should learn more and more about it. Question is, can you eventually take optimal actions? So this is the reinforcement learning problem. We can look at it a little bit more formally. So it's good to contrast RL, right, or reinforcement learning, with the planning problem in MDPs, which is what we covered in weeks 4, 5, and 6. So again, right, in the planning problem, you are given the entire MDP in a compact form as an input. Okay, you're given that you have 10 states and 5 actions, and here are the transition probabilities and rewards. That's your discount factor. Now find me pi star. So what we're solving there is a computational problem. It happens entirely, let's say, in the agent's mind. In the learning setting, on the other hand, the agent actually has to go and gather some data from the so-called real world. Okay, it's not purely doing something in its mind. That's because it only knows, let's say, S, A, and gamma. Sometimes, we'll assume it knows R. Sometimes we don't. Nonetheless, the crucial thing is it does not know the transition function T. Okay, so the only information it gets about T is when it takes an action in the world, right? It will go to a next state based on T. That we can believe, but we don't know what T is, right? So you end up going on the previous slide from S1 to S2. You saw it. You didn't know that that was a 3/4 probability transition. Okay, so that's the difference. And in the learning setting, the goal is still the same, right? We want to find out enough and take optimal actions. So let's just formalize it before moving on. So let's use the notation H, like we've done with bandits, to denote histories. So HT, right, at time step T is the history S0, A0, R0, S1, A1, R1 through ST. Okay, so when you begin, actually, you just know that you're in this particular state. You don't know more than that. Formally, we can think of a learning algorithm, okay, as a mapping from the set of histories to the set of either arms, which would make it deterministic learning algorithms, or the set of probability distributions over arms, okay, which would make it more generic, stochastic, non-deterministic, randomized learning algorithms. So that distinction you're already familiar with. We did it with bandits. Nonetheless, okay, the idea here is the agent can remember what it has seen because that conveys some information about the underlying MDP, right? And use that to decide what to do next. Okay, and it should ideally get better over time. Okay, if we do our job right, then we must have a learning agent that is able to improve its behavior with time. So how do we make this more formal? Here is how. The question is, can we construct a learning algorithm L that satisfies the following constraint? Okay, so let me explain what's going on here. Remember that a learning algorithm takes in a history HT and outputs, let's assume in general, a probability distribution over actions. Okay, so the action AT, right, that is going to be executed at time t is decided by the learning agent as a function of the history up to that point. Okay, so AT, let's say, is drawn from the distribution that is given by the learning algorithm. Now the question is, we are in state ST, okay, at time t. Is AT an optimal action for ST? So we know that there is an underlying MDP, and therefore there's an optimal policy. Maybe there are multiple optimal policies. So is A, right, among the optimal actions from that state for that MDP? What we're adding in a big sum over time, right, in the numerator is the probability that AT is actually an optimal action at time step t. Okay, and so for this sum to be large, right, with higher and higher probability, the learning algorithm must be taking optimal actions. Okay, and then what we're doing is we're dividing by t, right, and taking the limit of that as the horizon goes to infinity. Question is, will this limit go to 1? Okay, so let's also maybe rephrase this in terms that you are familiar with. So if you sum over time, over the entire horizon, the probability that you're taking an optimal action, right? This is the same as the expected number of optimal actions that you will take through that same horizon. Okay, so the question is, will the expected number of optimal actions you take as a fraction, right, go to 1? Or the other way around, will the expected number of non-optimal actions as a fraction go to 0? Okay, and this is how we defined it for bandits, right? We said we wanted the expected regret to, the fraction of regret over time, right, to go to 0, or the other way to say it was, we wanted the regret to be sublinear, right? So, I mean, when we defined regret, we were multiplying suboptimal actions also by the amount of regret each of them contributed. But nonetheless, right, we are basically asking the same question here. Can we be sublinear in the number of non-optimal actions that we take in the limit? Okay, so I'm not making it very explicit here, but naturally we would like to have a learning algorithm L that manages to do this on every input MDP it is interacting with. Okay, I mean, you can always do it for one particular MDP by sort of magically just following an optimal policy for one MDP, right, which is going to be sort of sublinear in its suboptimality. Which is going to be linear in its suboptimality on other MDPs, right? We want this to happen on every input MDP. Okay, that's our target. Okay, this is really as technical as we get this week. We will come back, right, with our technical discussion of solutions and such starting week 8. Okay, but what I'm going forward with is telling you a little bit about the various topics that we are going to cover as a part of solutions, okay, to the reinforcement learning problem. So we will get begun with the most classical topic of temporal difference learning. Okay, so temporal difference learning is the idea of learning based on every bit of experience that the agent gathers, right? It goes from state to next state, right, by taking an action and getting a reward in the process. So SAR S prime. You've learned a little bit about the MDP because this happened, right? How do you go back and update your knowledge? That's what temporal difference learning allows you to do. And we will consider two versions of the problem. Reinforcement learning, in the reinforcement learning vocabulary, you should be familiar with this. We talk about prediction and control. Okay, so when you say prediction, also known as value prediction, it's a little bit like policy evaluation. Okay, so we are, let's say, following a fixed policy, and what we want to estimate is the value function of this policy, or maybe sometimes an action value function. So that's the prediction problem. So when you're doing control, in tandem with this, you're also trying to change your policy, right, and trying to take actions that give you better rewards. Okay, so you're learning about values, but you're also using that knowledge to take better actions. Okay, so this is temporal difference learning. This will take up some of our lecture time, and then we will encounter the big gap between theory and practice. Okay, all through our discussion of MDPs, we have assumed that the number of states is n, the number of actions is k, and that these two numbers are finite. Right? When we, for example, designed our algorithms, we were happy when things were polynomial in n and k. Now, in reality, n and k can be at least n, right? Usually can be very, very large. Okay, it can even be infinite. So, I mean, if you're thinking of playing chess, right, you have a discrete state space, but that number of states is so large, there's really no way you can have a data structure putting all your states, right, as a sort of table or something like that. So, in practice, you will almost always have to generalize across states. Okay, so when you're learning something from one state, you will have to sort of carry that forward to neighboring states, so to say. Okay, and so this is what's covered in the topic of generalization and function approximation. It's actually in this context that we will start reusing, right, or drawing some parallels with supervised learning. Okay, so you need to use some compact representation. You might use a neural network, you might just use a linear function of some features, but then the sort of updates you will do, right, the way you handle it sometimes, right, will go through the supervised learning route. So it's a good idea for you to brush up a little bit of your supervised learning by the time we get to generalization and function approximation. Somewhat different class of methods which in principle sort of bypasses the learning of values, right, is called policy search or policy gradient methods. Now, the idea with policy gradient methods is finally what we want is a policy that's giving us lots of reward, right? Now, do we necessarily need to estimate the value function of this policy in entirety in order to induce the policy? Maybe not. Okay, so there is actually some theoretical basis and a lot of empirical support to say that you might actually be better off in some situations by directly searching over the policy parameters. Okay, you set up the policy as a parameterized function and see which parameters give you policies, right, which are able to give you lots of reward without, as an intermediate step, estimating the entire value function of the policy. Okay, so we'll look at policy gradient methods. We'll cover at least two other aspects of two other families of methods for reinforcement learning. In fact, one that we will begin with, which is very intuitive, is called model-based algorithms. So with model-based algorithms, the idea is quite simple. Okay, so we don't know the underlying T and R, right, transition function and reward function. So let's go ahead and actually estimate them, okay, from experience. And once you have estimates, right, you act as though you're doing MDP planning, okay, because you estimated T and R, right? With that, you have SA, your estimate of T and R and gamma, so do planning, okay? I mean, it's not as straightforward as that, but that's the basic idea. With batch reinforcement learning, which is yet another family of algorithms, it stands really in stark contrast to online reinforcement learning like temporal difference learning. The idea is you will remember your history, okay, for some time, and when you're updating your knowledge, you will do a more computationally intensive, usually, okay, update to your knowledge. With temporal difference learning, right, you're literally doing like one small update, tweak your knowledge based on what you have just seen, right? But with batch learning, you do multiple passes over the batch of data that you have gathered, right, and do a more substantive update. This sometimes goes hand in hand with function approximation methods such as neural networks. Okay, so this is again something that we'll cover in one of our subsequent lectures. Yet another one is called Monte Carlo tree search. Okay, abbreviated MCTS. So MCTS is a little bit different. Okay, so the idea is in many problems you actually have access to a knowledge of the model, right, or the MDP in some form. Okay, so for example, the classic example is board games. Okay, so let's say you're playing chess. You know the rules of chess. Okay, you know that when you take a particular action from a particular state, this is what is going to happen. let's assume we also know the opponent's strategy. Okay, so in some sense, you know the model. Okay, the transition probabilities and rewards. So they are not given to you in a form that you can do too much with. You can't really like solve for the entire optimal policy just because of the sheer sizes. Okay, so the number of states is so large that you can't, let's say, do value iteration and solve for pi star. However, you can do something to that effect from your current state. Okay, when you're actually in a particular state, you have to decide which action to take. You might have 5 minutes to make your decision, right? So in that 5 minutes, you can do some planning and at least approximately try and figure out what's a good action to take from this state. Okay, so if you're doing that, how do you do it? Okay, so Monte Carlo tree search is a very successful strategy that's been around for the last 5-10 years, right? And it's become increasingly popular in many of these applications. If we have the time for it, we will also look at multi-agent reinforcement learning, which sort of questions the Markovian assumption, but still there are algorithms for dealing with how to learn when there are also other learning algorithms in your environment. Okay, there might be more than one agent. They're trying to compete or cooperate, right? How do you learn? Last but not least, I hope that we will have some time to look at applications that are constructed by putting together many of these ideas. Okay, so the most significant successes, right, which have really made reinforcement learning a household name, really in many circles, is successes in game playing. Right, AlphaGo is a program that I'm sure many of you have heard about. There have also been successes with various types of computer games. So I'm hoping that we will have time towards the end of the course to go over some of these examples as end-to-end case studies, okay, which tell you a little bit about the practice of putting these different concepts together. Okay, so this is what's coming up in the remainder of the course. And why should we be studying reinforcement learning? Okay, so does it have practical applications? What really can we do after learning all of this theory? So I want to give you a few examples to drive home the fact that reinforcement learning is becoming extremely popular in terms of a practical approach to solving many problems. Okay, so the classical example with at least inside academia, most people are familiar with, right, is games. Okay, so games are easy, right? They're not easy to play. They're easy to describe and to work with as experimenters because usually they have nice simulators, etc. They're not as complex as the real world, but by no means are they easy to solve. Okay, so if you're looking at Go or chess, the number of states, right, and the number of possible things you can do is so large, which is why it's a challenging problem. Okay, so some of the earliest successes for practical reinforcement learning were on the game of backgammon. Okay, this is backgammon where you roll a pair of dice and move forward. Right, it's a two-player game, zero-sum game, and temporal difference learning, which is one of the topics we will get started with, was shown to successfully solve and get backgammon players that could play as well as humans. Okay, this is way back. This is from the 90s, in fact. Okay, and that's only gotten better. Go, right, is another program which was a much harder challenge, and that was successfully breached 4-5 years back. You've heard about AlphaGo, and thereafter, the same program that was used to play AlphaGo has been tweaked a little bit to also play chess extremely well. Okay, so we have very successful reinforcement learning algorithms for these games. It's worth mentioning that chess was originally solved in the 90s. Deep Blue, for example, right, that beat Kasparov was not really done using standard reinforcement learning, but similar ideas. You've already seen the example of helicopter control. Okay, so I gave you this as an example in the context of formulating MDPs. Now the question is, you can formulate it as an MDP, all right, but then can you solve it using value iteration or policy iteration? The catch is that the model of helicopter flight, right, actually involves the real world, right, the laws of physics. So from a particular state, when you're taking an action, right, there's friction acting, there's drag and lift and various other forces. do you actually have a good simulation model of this, or would you rather actually run the experiment on a real helicopter and use the actual data from there, right? So this is a design question, and quite often you don't have a sort of analytical model that you can use. Okay, so in fact, this reference here is an example where a helicopter was actually flown, okay, by a trained pilot, and data was gathered about the transitions, and a model inferred, okay, and thereafter used for planning. Okay, so it makes more sense to solve this as a reinforcement learning problem than as a MDP planning problem. Okay, video games, I've already told you, is a very popular application. It's got a lot of appeal. Maybe I don't have to be explaining that to the generation of students, right? Many of whom are also very familiar with what's going on with the video gaming world. But the basic idea is, in many of these games, you have agents, right? It might be a soccer player, it might be a car, right? It might be an agent that's doing something else. And so, most often, the human player is controlling one of these agents. You would also like to have the other agents in the game, right? Non-performing characters play reasonably well. So you can train many of them using reinforcement learning. Completely a different side, right? So any significantly complex system, right, has a lot going on. Okay, there's a sort of dynamical nature to it. So this is the top view, not of New York City, but motherboard, okay, of a machine, and you can imagine like the number of instructions going back and forth. It's really not possible for anybody to model in a totally convincing way. It's just got so much complexity, right? So you'd much rather have an agent sitting inside this, looking at how something behaves, right, and over a period of time, figure out how to optimize its behavior. So here's an example of doing that with the control of memory. Okay, so in an example like this, the state of the system is, so if you are writing a memory controller, you will record things like how many read and write commands are waiting in your queue, right? How long back did you perform some operation, etc. The actions will basically be, do you schedule this command for reading right now, right? Or this command for writing, or you do something else, right? So the design of the MDP comes from the domain in this manner. But what you would ultimately like is to maximize throughput, right? Any memory controller will have some bottleneck. There'll be more requests for memory than you have time to service it. And so you can maybe make a few reads wait, right? Because the write is happening, and then if you schedule it, you might get more throughput out of it, right? Without letting your programs starve for too long. Okay, so it's not only like inside of your computer, right, controlling memory, but in virtualization, right? When you have like a cluster, a data center on which you're running virtual machines, right? How do you schedule those, right? Many of these questions, right, because of the scale and complexity, I mean, human intuition and policies that we design can only go so far, right? But then if you automate it and allow reinforcement learning to actually pick up the crucial patterns in the transition probabilities, then we might be able to do a much better job. Okay, so I'm just giving you illustrative references. There are many more in each of these categories. Yet another one, which is surprising to some, is the use of reinforcement learning in healthcare. Okay, so here this reference has to do with using reinforcement learning as a way to treat epilepsy. Okay, so what happens in epilepsy is there is sort of uncontrolled electrical activity in the brain. Okay, so of course there is electrical activity in the brain all the time, right? That's the way we are able to do anything with our brain, right? To sort of think thoughts, right? To feel pain, etc. But when that sort of goes into overdrive and it sort of is uncontrolled, that's when you have an epileptic seizure. So one way of controlling epilepsy, right, is to give a small amount of electrical stimulation to the brain at regular intervals. Okay, so you give small stimulation so that the big thing doesn't happen. Okay, so that the floodgates don't open and you don't have an epileptic seizure. But at the same time, right, giving these small voltages at a regular frequency is also not desirable, because over a long period, right, if your cells are getting electrical activity that's coming externally, that's not good either, right? That can harm them in some way. So the question is, how can you minimize the amount of stimulation you give, right, so that tissue damage, for example, does not happen. But at the same time, right, you want to prevent epileptic seizure. This is exactly what was demonstrated in this paper from 10, 12 years back. This was, of course, done on slices of animal brain, okay? I think rat brains, but has shown very promising results. Okay, so you can see again, right, there is a control problem underlying it. It's not very easy for us to, let's say, build a computer model of how the brain works, right? But you can actually conduct this experiment on a real brain, right, or a good enough simulation of it, and then have a controller, right, a policy that is able to do this well. And the hope is you will then be able to take it back to real world. Finance, okay, so there are various divisions even within finance in which reinforcement learning is applied. This again has to do with the fact that it's a dynamical system, right? So one example is trading stocks. Okay, do you buy or sell? Usually those are your two actions. You do that as a function of state. State being, has the stock price been going up or down? What was the news, right, that got published yesterday, etc., right, which might indicate how the market is moving. Doing it now. Okay, this paper is from 20 years back now. It looks almost right, and policy gradient approaches is what is proposed here, and I know that that's also what's used quite often in industry. Okay, so I've given you a bunch of examples. I hope to drive home the point that there is sort of application of reinforcement learning. Now, I might be able to go into one or two of these. Okay, we really won't have the time to spend so much understanding applications, how they are modeled. But I've given you the references, and I hope you will follow up by looking at some of these references, okay, based on your interest. Okay, so that's what we've done today. We've not really gone into the actual solutions, but I have formulated the reinforcement learning problem and given you something to think about. Okay, so can you think of how to design that learning algorithm L that does a sublinear amount of non-optimal decisions in the limit? Okay, at least we'll get started with that, and then we will go into the more standard set of topics for solving the reinforcement learning problem. And when we do get the chance once or twice, also go into applications as a part of this course. Okay, all right, so this was a somewhat short lecture which has just come to conclusion. Let's meet again in week 8. All right, bye.